Hello everyone, it's September 13th. My lord, another difficult one. Haven't even finished deal with the previous ones. Alright, reconstruct itinerario. Itinerary. You are given a list of airline tickets where tickets I is from to represent the departure and the arrival airports of one flight. Reconstruct the itinerary in order and return it. All of the tickets belong to a man who departs from JFK. Thus, the itinerary must begin with JFK. If there are multiple valid itineraries, you should return the itinerary that has the smallest lexical order when read as a single string. For example, JFK and LaGuardia has a smaller lexical order than JFK and LGB. You may assume all tickets form at least one valid itinerary. You must use all the tickets once and only once. And from length tickets is 2, so everything is 3 letters long. Yeah, it doesn't really matter, it's just a bunch of nodes, and then we want to create a graph that will go through everybody once. So in this case, we can draw it out. Oh, that's only one way to go. JFK to this, this to this, this to this, only one way, right? But this, we can go, where JFK can go to here, and hold on, they say every ticket, right? You must use all the tickets once. So JFK to this, that's 1, that's 1, that's 1, that's 1, that's 1. So JFK to ATL, and then from ATL, we have 2 choices again. We can go back to JFK, or we can go to SFO, right? So whichever way we take, how do I? I mean, you can say what we want. We start from JFK, right? And we want the minimum going this way and going this way. And how do we know which one is better? Huh. How do we know? Oh. Yeah, you start from something and you have 2 paths, right? And well, some paths might not. Would it be possible that some paths that does not lead to the best outcome? I don't know. All tickets form at least one valid itinerary, but it is possible that if you go like, say we go greedy, we want to go with the smallest, and then go with the smallest is a dead end, right? So you probably need to go everybody else coming back and do this at the end, because you have to hit every single one. So the idea should be starting from one thing, give me the smallest to traverse everybody, right? Starting from 1, give me, and we also need a state. How do we represent the state of which path has been taken and which path has not? What data structure can we use to represent the state? I mean, yeah, but adjacency list or like backtracking. Backtracking. Can we do this with backtracking? We just, doesn't really matter. We start with one and then we start with one and eventually we will have to, but we still need to know which path has been taken and which path has not been taken. So 300 times 300 is 90,000. It's not that big. So maybe we can use a, well, that was, so like this, so like we have SFO, JFK, ATL, JFK, ATL, right? We create a this. So we have JFK, so it'll be row to column, okay? So JFK to FF, so the JFK, so this is 1, right? And then JFK to ATL, that's 1, right? That's all the JFK goes out. And then from SFO, go out to ATL. SFO go out to ATL. And from ATL, go out to JFK and SFO. So JFK and SFO. So that's kind of how it looks like. And then when we go through, we just check, right? If it's been taken, we take it to 0. If it's not, then we would it be possible that if we like more than one pass? Oh, that's actually not going to be useful. It doesn't really matter. All right, if it's more than one path. Ooh, it might actually be, hold a second. I don't know. Would that be a valid thing if we have, let's say, more than one path? Let's just throw JFK to SFO again. Actually, how about ATL to SFO? ATL to SFO. Yeah, let's just, do one more. See, is that gonna happen? Invalid input. So it cannot happen. But I guess you don't worry about it, right? So we use this data structure to record which path has been taken and which has not. 300 times 300, I think we can hold that. And then what? And then we just, so far the only way I can think of is simply to do backtracking, right? Backtracking, and then we try to see, well, to also track how many paths are left. Has to be 0, right? Has to be 0. If I'm adding at some point and then we try to go and we cannot go, then yeah, it's not gonna work. Then we try something else. And does Java has, I like this one actually, I remember this one. Does Java, yeah, I probably would need to read this. Hold up, let's see this. Java string comparison. Compare two strings. How about larger two and smaller? This is just compared equal. Hold a second. That's not what I want. String. Yep, this one. compared to. My God. The result is a negative integer if string object precedes the string object precedes the argument. So this is smaller than this. The result is a positive integer if the string object is lexicographically follows the argument. Result is 0 if they're equal. Yep, I think that is exactly what we need. This thing. Okay, so that's that. You want to give it a shot? No. Alright, so a list of strings. Yeah, that's fine. So what's gonna happen is, well, we're not gonna really, that's gonna be a void. We're not gonna return anything. It's just a backtrack function, right? So what we need is, oh, dude. You also need, oh my goodness. A hash map of a hash map. That doesn't sound nice. But how do we create that thing? Well, you need a list of all. Oh, I need a list of all. Otherwise, you're hash mapping it. Which I guess is fine. Yeah, why can't we do hash map? Why can't we do hash map? So instead of doing this, we do a hash map, right? So we say SFO, another hash map, right? ATL. Right? SFO, we go to ATL, and then JFK, we go to SFO, that's 1, ATL, that's 1, and ATL, go to SFO, and JFK. Right? Or even better, oh no, this is better, because there might be, no, 2 paths. In fact, we can do 2 paths. If we do ATL to SFO, we need to do SFO to ATL. So if we do this, and we do this, that will be a valid, because we just go through them. In that case, we do have to do it twice. Ugh. Yeah. Yep. Right. Okay. So you basically it's a counter. It's a counter. All right. So we need to do this. We call it a map of string to a map of string to integer. Right. So that is, we call it the graph. Okay. And here, what we have is the airport. AP string airport. And we also need to pass the number of tickets remaining, right? Remaining ticket. And let's do this, right? And we also need a list of string will be the result, and we'll have a string res str. It's important. So I'll say airport, and then we go to the last airport, and then remaining tickets becomes 0, right? So I say rem if remaining tickets is equal to 0. Yeah, now it's basically just backtracking, right? If it's a 0, oh, we also need a list string of itinerary, it, right? So now we need to Java join list of strings. Nope. String.join. String.join. Hold on. Do I have? Actually, it doesn't really matter, right? Because it says. So can I say it.join or string.join? Yes. Delimiter. What's the second argument? Iterable, right? So we say it itinerary. Let's call it out itinerary, right? Oh, it has to be a string. All right, can we do that? It's ignored. That's fine. I'm going to say string current equals this. If current dot compared to res str is smaller than 0, that means res str equal to current and res equal to itinerary dot copy. Do we have a copy? I don't know. Do we have a? How do I copy a string? How copy a array list? New array list itinerary. Okay, so that's that, right? Else, if it's not, then we have to check, right? Then we are at airport, right? We're at airport. So what we need to do is to go through all the keys of the next airport, right? Then we say for string next airport graph dot get airport dot key set, right? So we try the next airport, and what do? We will for the next airport there could be multiple. Yeah, I'm just worried. I mean, this is you're redoing a lot of stuff, right? You're redoing a lot of stuff. Ugh. But if this times out, then we will have to think something else. So the next airport, right? And then you're gonna just because we are going to go to that airport, right? So what we're gonna do is we're gonna first check if it's possible. If we can do this map string, right? Integer. We can say the subgraph, right, equal to graph dot this. So we have a subgraph, And then we could call subgraph.keyset if subgraph.get next airport is larger than 0, right? Then we can say subgraph.put next airport subgraph.get next airport -1. Okay, then we do backtrack next airport rem tick is -1 and oof itinerary dot add next airport, right? We add the next airport, then we go there, itinerary, then once we're done, subgraph dot put next airport subgraph dot get next airport +1, add it back, right? And then itinerary dot remove itinerary dot length, no, size -1, and remove the last one, right? So that's backtracking. And then we'll simply just say backtrack in JFK, remain tickets. Oh, you have to build a graph first, dude. We can say graph equals new hash map, right? And then we just say for list string from to of tickets and graph dot put if absent. Right, put if so a put if absent will give us a, so from to, hold on, we need to say string from equal to from to dot get 0, string to equal to from to dot get 1. So we have a from, we have a to, and we'll put if absent and put a from. If it's absent, then we say new hash map, right? And then we say graph dot get from dot put to and graph dot get from dot get or default to and default is 0 +1. I'll go through all this. We set up this, and this shall be tickets dot size, and that should be new array list. Blah blah blah. Then we shall return res. All right. Let's see if the small test case at least works, and then we will know that at least on paper. Oh. Yep, sorry, that's true, we haven't. So if res what's the default string? Is null. If res is equal to null, or okay, so we add this to it. My, it's not right. I'm not even having everything. Wait a second. Oh, I forgot the JFK at the beginning. Okay, so we can say list string itinerary shall equal to new array list. Right, itinerary.add JFK. And then this will do. I still want to see. I think I have initialize array. I saw this many times. Never worked for me. So you do that, okay. That is stupid. Arrays.as list. What if it's just one? Okay, let's try this. New array list. And arrays.as list JFK. Works. What if we do this? No. What if we have one? List off. Oh wait, it is list off. Array.list has to be multiple, right? Okay, it's actually not too bad. I forgot to put JFK in there. Alright, so now the only fear is this one will time out. Which most likely it will, because it's basically just brute force. Okay, that is a different one. JFK to KUL. Oh, you might not be in it. Yep, so we shall say if graph.get is null, right? We get it, so it will return null. Hold on. This one will return null. Oh no, it does not return. Okay, so we can just check, right? Or, nah, don't or. Let's just say if subgraph is equal to null. Yeah, I forgot, just return. Okay, so put this in. I feel like we're repeating a lot of operations. Yeah, okay, let's try this. Please do not time out. Give me a terrible runtime I'm okay with. No. Yep, this is timeout because we know this is brute force, it's timing out. That's fine. At least we have one solution. 3. So this is brute force backtracking. DLE. It's fine. Alright, so I think we have to figure out a way to represent this. So, what do you think? Say how many did we do? 11. Jesus. So how do we represent the state? The path already taken? No, it should be the path that... Now either the path already taken or the path that hasn't been taken. So if it's a path already taken, if it is the path already taken, how do we label it? So what does this look like? It doesn't really help. So even if we do that, there may be a lot of just which path has been taken. Now we have 300 of them. Okay, we have 300 paths. 300 paths. There gotta be repeats. Maybe the repeats is the issue. Yeah, there are repeated paths. Repeated paths. What can you say about repeated paths? Yeah, just a graph. Traverse all the edges in a graph. And then make sure the nodes follow a certain order. Doesn't really matter what type of order it is. I mean, all the edges. In some edges we can have duplicated edges. Or can we, hold on, let's see. We used to have a test case. I'd like to see that test case. Yes. This one and this one, right? This one and this one, the only difference is one has duplicate, the other does not. Because I'm starting thinking maybe we can remove the duplicate. Look, they are identical. So what does that mean? If you have a duplicate, right? If you have one path that's duplicated, what you're gonna do? If you have one path that's duplicated multiple times, which means you have something, just go there and you go there again, right? If you don't have the duplicate, so I'm trying to figure out if remove the duplicate, would the duplicate be of any value? I mean, you have some path from this to that, right? And then you say you can traverse the entire thing. Every has to be going once, which just means you have to go from here to here, right? And you have to go from here to here again. So if you don't have another one go from this to this, it's hard to say. I mean, it could be like you have another one on the other side and then you go through, right? So like you can just go through this multiple times. Oh God. All right, I'm out of idea. I need to see. DFS Eulerian Circuit. I don't know. I have no idea. Let's take a look. Oh, you gotta shitting me. That was so easy. All right, let's see. Eulerian Eulerian Path. Greedy DFS. Building the route backwards when retreating. All right, let's take a look. First, keep going forward until you get stuck. That's a good main path. Remaining tickets form cycles, which are found on the way back and get merged into that main path. By writing down the path backwards when retreating from recursion, merging the circles into the main path is Dude, I don't understand a thing you said. The end part of the path has already been written. Alright, this is useless. First time reading doesn't make any sense. Alright, let's see this example. To A, to C, to D, to A, back to A. Where we stuck. So we write down A as the end of the route. A is the end of the route, and then retreat back to D. there we see the unused ticket to B, and follow B, C, JFK, D. The written route is this. Then we retreat further along the original path. Prepending C, A, finally JFK. C, D. Because we go this, then we got stuck, right? Then we say we try to see here. And if we go this, and this, then we stuck. C, D, B, C, JFK, D, and then A. Let me think again. What are you saying? So we'll go greedy, because we always go to the smallest one. And we just keep going. So every time we choose the smallest one, and then if we got stuck. Then what do? We will backtrack. So like this path might not work, so we backtrack to this, and then from here we try to go again to find the remaining. Okay, now we find a path. It might end up at some position. Yeah, so we go, and then we got stuck. So the last path got stuck, so we back retreating to the previous one, and then from here we try to go, and then we all stuck again. Then we will retreat. Is that how it goes? Let's read it one more time. Keep going until you get stuck. That's a good main path already, because every time we go the smallest. Remaining tickets form a cycles which are found on the way back and get merged into that main path. By writing down the path backwards, when retreating from recursion, merging the cycles into the main path is easy. The end part of the path has already been written, and the start of it hasn't been written yet. So just write down the cycle now. Alright, let's see other people's comments. Any path would dead end at the final destination. Yes, any path it should dead end at the final destination. And building on that insight leads to a better understanding of the solution. It should help to see how targets is updating at each step. First point at which we got stuck. Update route. Search forward again until stuck. Update route. Wait, what does this update route do? Okay, this I don't understand. This I understand, right? So you keep going and you got stuck. But eventually you will get stuck at some point. So if I pre-stuck somewhere, then I say, okay, I don't worry about you at the moment. So I remove you. So I go backwards and I try go again. And if I got stuck again, right? If I got stuck again and there's still something more, then I can say I backtrack and I keep that. Then I go again. So eventually I got stuck. Yeah, like what does this mean? Okay, I don't understand this. Yep. When we stuck the first time, we have our final path. Why? Why? What do you mean when we have our final path? But there are loops in our path that we need to consider. Backtracking will start giving us loops. That's what you're seeing when we remove. Okay, I don't understand. Try another one. Eulerian path, there must exist a start node and an end node. Okay? Which means you can just go through everything and you end at some point. The end node can be the start node, another, yes. End node is start node if and only if all nodes have even degrees. What? A node is another node if and only if there is another odd degree node and the start node has an odd degree. Is to find the end node first and delete the path to this node. I still don't understand. What the hell? Have odd degrees are the entrance or exit. Entrance or exit. Odd degrees. Wait, what's this degree mean? Is it number of in or number of out? In and out. Then either it's an out, because you have out and in and out. Okay, that makes sense. They're the entrance or exit. In your example, it's JFK and A. JFK has 2 out and 1 in, so this must be an out. A has 2 in and 1 out, so A must be an in. Everybody else has the even number. Holy crap, that is true. So A has to be the end. You're kidding me. Which means you already know which one is the end. Hold on. What you're saying is you start with JFK. So JFK got to be, and they have only there should only be one end node, right? There can only be one end node, because if you have multiple nodes that have odd number of degrees, right? Multiple can be the end, then yeah, it doesn't work because you have to go through every single one, right? Yes, that's why your first try, you hit the end. That is the end. That is the end. So you go the first route, you go to the end, okay? So when you go to the end, that is the real end. But it doesn't work because you might not have hit anybody else, so you need to backtrack, right? You go to the previous one, right? You go to the previous one because in the initial one, right, you go, I don't know, right? And then you need to, okay, this is the destination, right? That is the destination. You already hit the destination. So what you need to do now is go back, because a solution would definitely exist. So you go back, and then you try to code again, right? And try to go again, and then because this is the only end, right? And everybody else have even number of edges. Even number of edges. In the JFK, you already used one, so JFK has even number of edges, even degrees, and everybody else all have even degrees. So if you retract that and you go again, go, and then you will, boom, you will end up at this, and then that's when, yeah, it will become a circle, a cycle. Okay, so that's my understanding. How are you gonna code this? Well, I'm gonna do, just go to the next. No, go to the next. It doesn't really matter which one you go, actually. Oh, well, it does matter, because you want to go to the smallest, right? You want to go to the smallest when you have multiple choices. All right, when you have multiple choices, you want to go to the smallest. That's the greedy part, right? That's the greedy part. So you go to the smallest, right? And then if you're standing from here, you look at the next, and you need to go to the smallest as well. Okay, do you use priority queue, or how? Oh man, it is priority queue. Damn, it is priority queue. So, okay, so priority queue to store all your next destinations, okay? So every time you go, you'll pick the smallest out, and then you'll go again to the next one, to the next one, to the next one, until you hit a point where, because every time you do it, you pop it out. So now, at the end, there's no more. So you hit the dead end, okay? You hit the dead end. Now you need to trace back, right? You need to trace back. So basically, I can pop it, right? I can have a itinerary as we go along. We just add, and then the last one I can, so I just pop it, right? I pop it. Now we go to the previous one, right? We go to the previous one, because previous one I just said go to the next one, right? And after I go to the next one, I come back, I can return true or false, right? I can say, not really return true or false, I shall return, what do I return? we can have a global value to record the number of edges left. Okay, we report the number of edges left. So when we go to the end and the number of edges left is more, then what you do? You that's the last one. So you pop it, but you don't put it back, right? So every time you go, you pop it. You pop this. You pop the smallest. Then you try to go there. And then once you hit the dead end, you save the dead end, right? You save the dead end. And then you just return, right? You return, and this edge is gone, but this edge is no longer in consideration, right? This edge is no longer in consideration. So you go back and then you try it again. So yeah, so basically I remove this edge, right? And then we go again from here. Then we go this, boom. Now we go to the end. And we just put this at the end. Okay, you want to give this a shot. I'm actually not quite sure if it's correct, but we are going to give this a shot. So without reading his actual implementation, let's resort to default. All right, we need, actually, no, I should, come on, don't do this to me. We will use some stuff. This is like a DP, not DP, it's a DFS, right? So this, we call it DFS. Okay, DFS. We'll deal with this one later, doesn't matter. And then this is, can do it. The method is inspired by I'm not gonna deal with this at the moment. What I'm gonna do is just try to see if it works. This is a hash map, but that is a map of string. We don't need this. We need a priority queue. Okay, priority. Wait, hold on. Where's priority queue? String. All right. How do I do priority queue in Java? Java priority queue. Priority queue. Wait, hold a second. Add poll. Oh, add poll. Can I do string? It's always a min heap. Wait, hold on. In the below priority queue, an element with a maximum value will have the highest. Your queue content. You're kidding me, right? It's a max queue. No. It's the least element with respect to the specified ordering. Arbitrarily. Yeah. I think it's a main heap. Let's see. 10, 10, 15. Yeah. It's a main heap. 4 geeks. Okay, that's fine. So we're gonna have to first build it. A hash map for this. From to put absent shall be new priority queue, right? And we'll get this dot add 2. That's right. Okay, so that's how we build a graph. And then we are going to do, what are we going to do? We're going to do DFS, right? DFS is a start. Actually what I want is, I think we can do list string res equal to new array list. Actually, we do this, right? That's fine. And then we put the res in it, just trying to extend it. Or we can just do an empty and then we'll add it first. And then this, we probably don't do it this way. Like a global, right? So we're adding. Every time we get a node, we add to it. Every time we get a node, we add to it. And then when we get out, no, I don't think we need it. Okay, let's try. So DFS, we have string, we have the graph. We don't need this, nor do we need this, right? And then we'll do DFS and I'll return. Okay, so I think this is fine. So now every time when I come here, right, every time with DFS, so the first thing we do is we will call this dot add airport, right? We'll add the current airport, and then what? We'll add the current airport, and then we'll go to its map to see if there is another one, right? If there's another one. But how do we know we are not at the end? So I kind of do need an integer, remaining tickets, right? So I do need that. So we can say remaining tickets shall equal to tickets dot size, right? And every time we add an airport, that means one ticket is gone. So we say remaining tickets minus, right? And we will go through, right, the priority queue. We'll go through the priority queue for the next one. So I have this one, and we'll see if it's empty, right? If it's empty, that means we're at the end. So we also need the end. So string dest, call it end, right? We'll have an end. If remaining tickets is not equal to 0, and graph dot get airport, right? Because when the current airport dot get airport. Q. Let's do Q. Priority Q. String. Right. Q shall equal to graph dot get airport. If Q is not equal to null, and Q dot is empty. Right, so this is, we have reached the end already. So in that case, we say end equal to airport, right? And then we are going to return. But remaining tickets, we don't go back up. We simply just return. Right, we simply just return. We record what is the end, then we just return. Okay? Else, right? Else, now we just, go through. We say while Q and Q dot is empty. And not Q is empty. Is not equal to null, and it's not empty. Then I say string next airport shall equal to Q dot poll. Right? And then we say DFS next airport. Oh, I need to add as well. Itinerary down. No, we don't add it here. We go to this. Oh, we need to pop. Itinerary dot remove itinerary dot size -1. Yeah, we need to remove that and then return. So we do that, right? And then if it's not good, we'll come back and we'll do it again. Try to do it again, we do it again. And until at the end, we will get the remaining tickets, get back to 0. Yeah, so like at this, we'll eventually go back to D. I see the JFK, and then JFK has another one. The JFK, we have another one, so we go to D. And D will have taken all the routes, and then D have no routes. So this gets out. Basically just return. And now we return here, we're going to have no routes. So yeah. So none of this is necessary. Right, so with DFS, right, DFS, DFS, DFS until the end. Then what we need to do is, when we get out, res.add end, then we return res. How does this one look like? Not sure. Let's try these. Does it work? Nope. I have a null. And it's not equal to null. Let's just put this one in as well. Nope. I think the understanding is not right. I don't know, man. I mean, if you look at it, the end is different. This end is JFK. This end is SYD. Can we have like a easier one? You know, just easier path. Don't have to go through the whole stuff. Let's try. What if we? I don't know, man. This will be tough. This won't work. Invalid input. Urgh. Shoot. Yeah, the thing is, you don't know. This is not gonna work. I have no clue what happened. Anyway, let's try. I mean, this. I thought we got it, right? We start from. Yeah, we go to the first one, right? And then we say remaining tickets is 0. Q is not equal to null. What if Q is null? That means we have someone that doesn't go out. We have someone that does not go out. But this definitely is. Maybe we should do this, because I think Q can be null. Right? If you're only receiving. Yeah, because you're at the end, right? You're the last one. So I can say if Q is equal to null, or Q is empty. I don't know. I hope this little change can save us. Nope. Yeah, I have more than what is expected. No, that's not. I have less. Okay, can we run a diff? So this is my output. This is the expected output. That is not helpful at all. But we can see the difference is it is the last line, right? JFK. I miss AUA and SYD. Missed the 2. There might be multiple. There might be multiple ends. Why would that be multiple ends? That doesn't make any sense. There shouldn't be multiple ends. There should be only one end. Yeah, but I am missing these two. Where does these two go? AUA and SYD. Oh, it's hard to put in here. Ah, damn. -1. Gordy. That ain't right. Huh. Wait, hold a second. We're not doing it right. Okay, so every airport I add it, right? And then the remaining ticket to do this. And we get that. And we say if the ticket's not 0, but so you're reaching the end, then the end, wait, hold a second. Do we get the end right at least? My end is JFK. The hell? So I didn't understand it fully. Yeah, so the first route, we end at JFK. And then we try the other route. Alright, we gotta read again. Yeah, it didn't work. Let's see again. There must exist a start and an end, right? We start over another node. End node is start node if and only if all nodes has even degrees. n node is another node if and only if there is another odd degree node and the start node has an odd degree. So the algorithm is to find the n node first and delete the path to this node, meanwhile using priority queue to guarantee lexical order. If the last two nodes are when it gets stuck. When the end node A is found, it is saved to the result and then returned to the last node when it is popped. I still don't understand. Mm-hmm. Mm-hmm. Can we have another one? Uh-huh. Maybe we can just understand this. You just DFS. You get a path on the outside. Flights. That'll get departure. Arrivals. While arrival is not null and it's not empty. DFS dot pass dot add first departure. What? What is this? I'll pull the smallest, pull the smallest, pull the smallest. So at the end, we'll reach the end. So we will put it in, right? That's the end. Then what? Then I because the previous level, okay, because I already go to the end. I go to the previous level, and at the previous level I need to go to the next one. Now I'll find hold on. I think what it says is if we keep going, the first end that we reach is the end. Right? The first end we reach is the end. Regardless, the first end, because there's only one true end. There's one true entrance and a one true end. Right? Therefore, everybody else has even number of in degrees and even number of out degrees. And then the entrance has more in degrees than out degrees. And if that's the case, then the entrance can only get out, and the end must have more in degrees than out degrees. But it also can be the entrance has even number, the same number of in degrees and out degrees, and eventually, because everybody will get in, get out, or get in, and then will get out, and eventually will always end at the end. But it doesn't really matter. So we start from the start, right? And then we go. Then we hit the end. The first end we hit is the end, is already the end. So we need to record it, right? That is the end. And then when we hit the end, we need to backtrack. So we hit the end. We know this is the end, right? But we don't know who is the second to the end. So we go to the previous one, right? Now the previous one, we already consumed one of its out degrees. And there is same number of in degrees and out degrees for that previous one. So if we consume its out degrees, then that becomes the new end. Right? Yeah, because we have more in degree than out degree. So that becomes the new end. So if we start from this, right, then we try to go, then we will end up, because we have one out, we're same in, same out. So then we'll definitely end back on this one, right? We'll end back on this one. Because everybody else yeah, so now we will start from this, then we go out, and eventually we'll end up at that one. This is the new out degree, right? Then not our new end, then we add it, right? Then the next, what we do is we backtrack. Whoever leads to this, now that becomes the new end. Sorrowful. Yes, I think this is a very important insight. Wait, hold on. Let me. I need to copy this. This is the real thing. All right, now we can go for. All right. So okay. So here's my understanding. Since one itinerary exists, there must be one entrance and one end. One start and one end. Right. The start is set to JFK. So no matter how we traverse the graph, the first time we get stuck, the first node that we get stuck on must be the true end, right? It must be the true end. Now when that happens, when that happens, we may or may not have visited all the edges, but we're sure that the end is found. We add that. We add it to the itinerary. We add the true end to the itinerary. Then we backtrack, right? Then we backtrack to the node right before that node that leads to the true end. Now here is a very important insight. A true, if a true end unless JFK has the same number of in degree and out degrees. In this case, JFK must be the true end. The true end must have more in degrees than out degrees. Right. Similarly, in that case, JFK has more out degrees than in degrees to serve as the true starting point. All the other nodes must have the same number of in degrees as out degrees, because otherwise we would have more than one true ends, and it will break the assumption that at least one itinerary exists that can visit all the edges. Now that we have added the true end and backtracked to its previous node, this previous node becomes the new true end, becomes a new end, because after consuming its out degree to the true end, it now has more in degrees than out degrees. I mean, that's not actually true, because you have to enter this and then enter this, and then starting from here. Yeah, that's not true. That's not really true. No, that is true. It is the new, yeah. Because it becomes the new end. Because for JFK, right, it has more out degrees than in degrees. So we do want that it should have the same out degrees and in degrees. This is because all the nodes now have the same in degrees as out degrees. JFK consumes one out degree, so it is balanced now. The true end is removed, right? So no other nodes has imbalanced in degrees versus out degrees. All the nodes now have the same in degrees as out degrees. Hence, if we start from the current node, we are bound to end at this node, right? Bound to end at this node. So we do that, right? So we do that because we need to traverse the others. Yeah. Start from the current node and DFS again to incorporate the other edges we're bound to end at this node. Therefore, we continue, right, the DFS, and when that is terminate, when that ends, we add the current node to the path as well. So essentially, the DFS part finds each end, finds the true end, then the end, then the new end before the true end, and then the new end before the new end, etc. Right, each time such end is found, it is added to the path. There is also a greedy portion, greedy component to the solution, where each time we only choose the lexicographically smallest node. Yeah, every time we choose the smallest node to visit. I kind of understand, right? I kind of understand. So this is still good. We don't need ticket size, okay? Yeah, we can do a result, but I think it'll be better to do the result on the outside. Okay, so let's do the result on the outside. Actually, I can just initialize it here. So we don't need this. I just do that. We don't need this. And we just call DFS, right? And we just return. How do I reverse? Reverse array list. Collection class has a reverse call. So okay, we can say collections dot reverse res. Okay. Ooh, what happened here? Provided void. Res is void? It shouldn't be void. Let's try. We haven't write this one yet. So this I just need airport, right? So we'll do this, and then we say while Q is not null and it's not empty, we'll get the next airport, and we'll get the next airport, and we'll get the next airport until we hit an airport where this is empty, right? So if this is empty, then we can say res.add airport, right? That's the last airport we add. This is the last one. Now we backtrack to the previous one, right? So the one's connected to it, and then for that one, we basically find the next one to traverse. Now we find a new cycle, right? We find a new cycle, and the new cycle will end at that one. And then we will basically go back to this airport and we'll have nothing. So that one, that's a new end. So we put a new end in it. So every time we just find a new end, we find a new end. And I don't know what reverse. Yeah. I have no clue why this one says I don't understand. provided null. Oh, the return is always in place. Dirt. Ah. Okay, so let's try this one. Yeah, it will work because I just copy and paste from that. Holy crap. Yeah, this is tough. I don't know. I don't know how this one is done at all. Okay, so it'll be it for today, but I need to read this Eulerian Path. I probably have to go more Wikipedia page as well. And have a Eulerian Circuit. Oh my god, there's 2 more things to learn. All right, I will learn. Oh Jesus. All right, I'll see you guys tomorrow. Adios.